So let us move on. Okay, so now we're going to look at a new relationship called Charles' law. So as I'm erasing this board, I'll talk about what Charles' law is. So what Charles' law is looking at the relationship between the temperature of a gas and the volume of a gas. And you're holding the pressure and the moles of the gas constant. Okay, so here is sort of a description by a picture of what this relationship would be. So let's say we have on the left side a test tube with some trapped gas. That trapped gas there is in yellow, and it's kind of trapped by a plug of mercury there. And let's say we decided to heat up the gas. And if we heat up the gas, what will happen is, of course, the temperature of the gas will increase, but its volume would increase too if the pressure and the number of moles of the gas remains constant. And so this is an expression of Charles' law. And so what I think you can sort of see is that if volume of the gas increases, that must mean the temperature of the gas increases. If volume of the gas decreases, then the temperature of the gas must decrease. Therefore, the qualitative relationship between volume and temperature of a gas is that they are directly related to one another. In other words, when one goes up, the other goes up. Now, what is the quantitative relationship between volume and temperature? That's pretty simple. As long as you look at temperature in degrees Kelvin, you can make statements like this. If you increase the temperature of a gas 2 times, its volume will go up 2 times. If you increase the temperature of a gas 3 times, its volume will go up 3 times. If you increase the temperature of a gas 10 times, its volume will go up 10 times. This only happens when you're considering the temperature of a gas in Kelvin. That would not apply if the temperature of gas is in Celsius. So that tells us something important. When we are working with equations with Charles' law, so that this relationship, this 2 times increasing the volume is 2 times increasing the temperature holds, we must convert any Celsius temperatures into Kelvin. Okay, so here I'm just kind of stating again sort of the qualitative relationship between volume and temperature of a gas is that when one goes up, the other goes up. Okay, so we need to talk about why is it that when you increase the temperature of a gas, why would its volume increase? And so you sort of need to know the explanation for that. So you have to imagine, say, a gas trapped in a flexible container. Let's say you started heating up that gas in the flexible container. What is going to happen? Well, the heat will make the molecules of the gas in the container go faster. And if they're going faster, they're going to hit the surfaces of the container harder. And so that's going to increase the pressure on the container. And so that's going to tend to want to push the container to be larger, to accept the gas. Now, what will happen is, in this situation, the pressure temporarily within the container goes up, but it'll want to equate with the outside pressure, which is less. And so basically, to get that pressure as it's temporarily going up within this flexible container to go down, it must increase its volume. So in the end, if you have a flexible container, if you increase the temperature of the gas so that you can keep the pressure in that container to be constant, the volume must increase. Okay, and so I want to talk about 2 important points of Charles' law that are sort of applied to real life, which you need to know about. So Charles' law explains why hot air balloons levitate. And so I want you to understand that. And so we now know that when we increase the temperature of a gas, it increases the volume of the gas. Now let's say that you have a hot air balloon. And so you know to get that balloon to rise in the air, you have to heat the air within that balloon. So you have some kind of fire at the base of the balloon, which heats the air. Why is it that the air balloon rises in the sky when you heat the air inside the balloon? Well, we know that when we heat up the air inside of the balloon, what will happen is the air will want to expand to increase its volume. So the balloon gets even larger and larger. Now, let's think about what's going to happen to the concentration of the molecules inside the balloon when that happens. If the balloon gets larger and larger, the concentration of the air molecules in the balloon will get less and less. There are few air molecules per space that there were before. Therefore, if the concentration of the air in the balloon is lowering, that means the density of that air in the balloon is getting less. Now, one of the things you learn is if you have two fluids, say two liquids or two gases, you will have the one with lesser density rise through the one with the greater density. So not only does this apply for liquids, it applies for gases. And so because the air within the balloon is hotter, it's going to expand the volume of the balloon, and so there's going to be less concentration of molecules. The molecules within the balloon are less dense than the molecules outside, and so that causes the balloon to rise through the air. Now, another thing which is kind of important you need to understand is Charles' law can be used to predict the temperature that you will have to get to absolute zero. So let me explain that. Okay, so let's say you have a gas, and let's say that what you have is 273 milliliters of a gas. You have that precise volume, and let's say this gas is at 0 degrees Celsius. Now, let's say you raise the temperature of that gas by 1 degree Celsius. What would happen to the volume? Well, you know if you raise the temperature of that gas, the volume should increase. So you're going from 273 milliliters to something higher. Well, it turns out if you're at 273 milliliters, you will go up to 274 milliliters. So let's make a graph of this really quick. So on the y-axis, I have volume of a gas, and on the x-axis, I have temperature of a gas. So let me just kind of expand the temperature axis here. Okay, so now what I'm going to do is I'm going to put here, this is going to be 0 degrees Celsius. And so at 0 degrees Celsius, we have 273 milliliters of gas. So this is 273 milliliters of gas. So if we go up 1 degree, what that means is the volume will increase to 274 milliliters. Now, imagine we went down a degree to -1 degree Celsius. So now we're at -1 degree Celsius. The volume will go down a milliliter. So now we're at 272 milliliters. If you go down to -2 degrees Celsius, we're now at 271 milliliters, and so on. You can see that for every degree we go down, we reduce the volume of the gas by 1 milliliter. So you might expect that there'll be a temperature that we'll get to that will be so cold that the volume of the gas can be brought all the way down theoretically to 0, meaning it's gotten so cold that your gas, which has some volume, has absolutely no volume at all. That temperature you need to bring the gas to get it theoretically to have absolutely no volume is called absolute zero. And so in Celsius, that temperature is going to be -273.15 degrees Celsius. And so this is also defined as absolute zero, which is 0 degrees Kelvin. Can we ever achieve absolute zero? And the answer is we probably never could. And the reason is this. Imagine that you have a gas and you're cooling it down. You're just lowering the temperature a degree after a degree after a degree after a time. And then you'll know at one point it'll get so cool that it will liquefy. It will become a liquid. And that will bring the molecules a lot closer together. And then you can cool it down further and it will solidify. And then that should bring in the molecules a little more closer together. So you can keep cooling it and cooling it and cooling it down. And so you'll get to the point where the molecules are as close as they can get. They're touching each other, but we still have a little volume left due to the molecules that are there. The molecules occupy volume. So in theory, because the molecules always have a little volume to them, we can never get it to a point where we have the molecules having no volume at all, which predicts that we can never get it to a temperature where you would have the molecules with no volume at all. So in theory, we never probably can get to a temperature of absolute zero. Okay, so one thing you need to do on a test is solve problems using Charles' law. So let me talk a little bit about that. So here is the relationship that you will probably be using in solving problems, that you have V1 over T1 is equal to V2 over T2, where V is volume, T is temperature of the gas, 1 is the initial conditions, 2 are the final conditions. And you're going to be holding pressure and moles constant. But very importantly, when you use this law, you must convert a Celsius temperature into Kelvin. If you don't, you will get the wrong answer. So let's go ahead, and I want to talk a little bit about how you might go about solving a Charles' law problem when it comes to dealing with significant figures. So there are a couple ways you can do it. You can do it the way you've been taught in Chem 109, is where you do calculations as you're going through the problem. You put a bar over the number that you would consider as significant, and then you carry the numbers through, and at the very end you round to correct number of significant figures. But there's another way you can correctly solve these problems. You can break the problems up into pieces, and after you've completed each piece, then you round to correct number of significant figures, and then you take that answer at that number of significant figures and you plug it into the next step. That's how your book does it, and so I'm going to, just to be consistent with the book, that's what I'm going to do. So for example, we have a Charles' law problem here, and the first step is to probably take some temperature in Celsius and convert it to Kelvin. So here I have an initial temperature at 125 degrees Celsius, and I have to convert it to Kelvin, so I add 273.15 degrees Kelvin. Now, what you can see is if you added those two numbers, what you would get on your calculator is 398.15. And normally you would take all those numbers and run them through any other calculations you need to do. But I'm going to do it the book way. I'm going to take the 398.15 and I'm going to round it right there to correct number of significant figures, which is 398. And then I'll apply it to the next step. And so the next step is using the Charles' law equation to solve for the new temperature, which is going to be it's 192 Kelvin. And then there, after that second step there in red, you round that to correct number of significant figures. And then maybe the final step is to take that Kelvin temperature and convert it back to Celsius. And so after the final step, I convert it to correct number of significant figures, and that should give me my answer. So let me go ahead and do this problem really quickly. Using the book method of rounding to correct number of significant figures. Okay, so what I have is I have a gas, and we have 250 milliliters of it, and it's at 1 atmosphere pressure at 25 degrees Celsius, and we're trying to find what volume it will occupy when we raise the temperature to 50 degrees Celsius. So let me go ahead and assign variables. So here I have a gas that had an initial volume of 250 milliliters, and I'm going to just put a dot there to indicate that these three numbers are significant. The temperature initially is at 25 degrees Celsius. We're trying to find what the new volume is. The new temperature of 50 degrees Celsius. Okay, so what we need to use is Charles' law. So let me write out what that is. It's V1 over T1 is equal to V2 over T2. Okay, so as I was kind of saying before, with these simple gas laws, if you have a temperature, you must convert any Celsius temperature to Kelvin, or if you don't do that, you'll get the wrong answer. So let's do that as our first step. So we're going to take this Celsius temperature, which is 25 degrees, and then we're going to add 273.15. And so if you take those numbers in your calculator, you'll get 298.15. But we're going to round it right now to correct number significant figures like the book does. And if you do so, here, rounded to correct number of significant figures, the temperature here should be 298 degrees Kelvin. Okay, now that we have our temperature in Kelvin, what we can do, well, actually, we have to convert this 50 degrees Celsius into Kelvin too, right? So we're going to add 273.15. And so this is going to be 323.15 degrees Kelvin. But again, I want to round this to correct number of significant figures. So it's going to be 323 Kelvin. Okay, now that we have our temperatures in Kelvin, we can solve for V2. So what I need to do is I need to change this equation around so that I have V2 in the numerator and it's by itself. So right now V2 is in the numerator. So all we need to do is move out T2. It's in the denominator right now. When I put it on the other side of the equal sign, it goes into the numerator like this. So what would be for V2? So V2 is going to be equal to V1 times T2 over T1. Looks good? Okay, let's plug in some numbers and see what we get. So we have V2 is going to be V1. V1 is 250 milliliters. And then T2 is 323 degrees Kelvin. And then here T1, need to put a 1 there, is going to be 298 degrees Kelvin. So you can see that the Kelvins cancel out, so we should get an answer in milliliters. And I think if you went ahead and did the math, what you would find is going to be a slightly higher volume because we're increasing the temperature. So the answer should be 271 milliliters. Okay, so let's move on.